In this research we delve into the quantum transport properties of two-dimensional electron gases, 2-DEGs, in the presence of both Rashba and Dresselhaus spin-orbit interactions, SOI. Our approach utilizes a Hamiltonian that combines these two types of SOI, and we employ a partial diagonalization method to solve the eigenvalue problem. This method allows for the calculation of the density of states and the function, which are essential in understanding the Shubnikov-de Haas (SDH) oscillations observed in these systems. We begin by describing the Hamiltonian of the system, which is a combination of the kinetic energy, Rashba, and Dresselhaus terms. The Hamiltonian is then rewritten in a block diagonal form, where each block corresponds to a specific Landau level index n. The partial diagonalization procedure involves constructing a partial matrix HPD centered on block n with NPD blocks above and below, allowing us to calculate the entire spectrum for each value of n. The density of states, DOS, is calculated using the Poisson summation formula, resulting in a DOS that highlights both fast and slow oscillations. These oscillations are described by the functions f plus and f, which represent the fast and slow parts of the SDH oscillations, respectively. The functions can be determined by finding the roots of epsilon n, s, b, equals EF, h omega c, where epsilon n, s, b, is the eigenenergy of the Hamiltonian, EF is the Fermi energy, and h omega c is the cyclotron frequency. Our results demonstrate that the introduction of Dresselhaus SOI leads to the formation of gaps in the spectrum, and anticrossings between states of different parity. These anticrossings are visible as rounding in the function, indicating the presence of both types of SOI. The function can be calculated using the partial diagonalization method, providing a detailed understanding of the SDH oscillations in the system. This work contributes to the understanding of quantum transport in 2-DEGs with mixed SOI, shedding light on the interplay between Rashba and Dresselhaus interactions and their impact on the DOS and SDH oscillations. The authors present a novel method for efficiently calculating the relevant energy spectrum in Shubnikov-de Haas (SDH) Magneto-oscillation analysis. This method combines numerical procedures with the Poisson summation formula, allowing for an efficient calculation and better understanding of fast and slow magneto-oscillations. The spin-orbit parameters alpha and beta, as well as the Landau level broadening gamma, can be uniquely extracted from F-, which oscillates slowly. The authors apply their method to realistic magneto-transport data, finding quick and accurate fit results for the slow oscillations. The method does not rely on finding beating nodes, making it applicable in cases where alpha and beta are comparable in size. The paper also discusses the spin-orbit interaction in a two-dimensional electron gas, 2-DEG, with both Rashba and Dresselhaus spin-orbit interactions, showing how the spin-orbit interaction introduces a new oscillation frequency F+ related to the spin-orbit interaction. The authors provide a detailed explanation of how to fit real transport data using their method, including the generation of realistic magnetoresistance data and the fitting process. The method is shown to be very efficient and accurate, with the resulting fitted parameters closely matching the original data generation parameters. The discussion on Gaussian broadening leads to an expression for the spectral density, which is then applied to equation 8, using trigonometric relations, resulting in equation 10. This section highlights the importance of spin-orbit coupling and its effects, referencing works by Shubnikov-de Haas, Bychkov and Rashba, and others. It also mentions recent studies on quantum oscillations, including those by Candido et al. And Hatke et al., showcasing ongoing research in the field. The mathematical derivations and experimental findings are crucial for understanding spin-orbit coupling and its implications.